start with the determinant of matrices. So we are going to restrict ourselves to 2 by 2 and 3 by 3. And we can only find the matrix of a square matrix. A square matrix is a matrix that has the same number of rows and columns. If the number of rows of a matrix and the number of columns are the same, we call that matrix square matrix, 2 by 2, 3 by 3, 4 by 4, and etc. So we are going to start with determinant of 2 by 2 matrix. So if you are given a matrix A as given here, then the determinant of A denoted by det A or bar A or something like the absolute value is defined by AD minus CB. So if you are given a 2 by 2 matrix, just multiply A. If you are given a matrix A, B, C, D, so to find the determinant, determinant will be A times D minus C times B. So we have an example here. Determine the determinants of the following matrices A and B. The matrix A is 1, 2, 0, 2. So determinant of A is 2 times 1 minus 2 times 0, which will be 2. So determinant of B also will be 1 times minus 1 minus 1 times 1. Determinant of B is 0. If the determinant of a given matrix is 0, we call that matrix a singular matrix. So if a matrix has determinant 0, that matrix is said to be a singular matrix. B here is an example of a singular matrix. So there are many examples of 2 by 2 matrices. It is very easy to find the determinant. Just follow the steps we followed here. So determinant of 3 by 3. So this is different from finding the determinant of a 2 by 2 matrix. Find the determinant of the following matrices A, B given here. So the determinant A is a 3 by 3 matrix. So to find the determinant of this 3 by 3 matrix, first label the elements in the first row, starting with the first one, plus, minus, plus. So label the elements, that is the first step. Label the elements in the first row, plus, minus, plus. Then you proceed as follows. The first element, if you look at our matrix, is 1. So if you delete the column of 1 and the rows of 1, you will be left with a mini matrix, which is a 2 by 2, which will be 5, 6, 8, and 9. Delete the row of 1, delete the column, the row of 1, delete the column of 1, you will have a mini matrix which is 2 by 2. So 1 times this determinant of this mini matrix plus 2 is the second element in the row, and when you label it, the first one was plus, 2 is minus. So plus minus 2 times, delete the row, the column of 2 and delete the rows of 2. You will be left with 4, 6, and 7, 9. So delete the row, the column of 2 and delete the row of 2. You will be left with 4, 6, 7, 9. So it will be minus 2 times the determinant of this mini matrix plus 3 there is positive. That is why we have plus 3. So plus 3 times, delete the column of 3, delete the rows of 3 also. You will have 4, 5, 7, 8. Or you will have 3 times the determinant of this mini matrix. So we have, remember, the first thing is label the elements in the first row. Start with the first one, plus, minus, plus. Then delete the column of 1, delete the row of 1. You will be left with 4 numbers. Then these 4 numbers form what we call this mini matrix. So 1 times the determinant of this mini matrix is the first evaluation, plus 2 there is negative. That is why I put it in a bracket. It's minus 2 times, delete the column of 2 and delete the row of 2. You will have 4, 6, 7, 9. or it will be minus 2 times the determinant of this mini matrix, plus 3, 3 is positive, plus 3 times, delete the column of 3, delete the row of 3, you will have 4, 5, 7, and 8. So this is how you evaluate the determinant of a 3 by 3 matrix. So 1 times determinant of this mini matrix is just a 2 by 2 matrix, and we show how to find the determinant of a 2 by 2. 5 times 9 minus 6 times 8, you have that, minus 2 times 4 times 9 minus 6 times 7 plus 3 times 4 times 8 minus 7 times 5. So if you evaluate, the answer will be 0. So A here is a singular matrix because the determinant of A is 0. So let me explain again. You have 3 by 3 matrix. To find the determinant, first label the elements in the first row, starting with the first one, which is plus, minus, plus. It's just labeling. Plus, minus, plus. Then take the first element in the first column, first row, delete the column of the first element, delete the rows of the row of the first element. You will be left with a 2 by 2 matrix. So it will be 1, that first element, times the determinant of this mini matrix, which is 2 by 2, plus, but 2 there in the labeling is negative. So you will have minus 2 times the determinant, delete the column of 2, delete the row of 2, you will be left with 4 elements. Find the determinant and multiply by minus 2. The last element is 3. Delete the column of 3, delete the row of 3. You will have 4, 5, 7, 8. Find the determinant and you will have, find the determinant of the mini matrix, and you have the determinant of your 3 by 3 matrix. So the determinant of A here is 0. So A is singular because the determinant of A is 0. So B also is the same approach. First, label the elements in the first row, then make this, delete the row of this, delete the column of this, and find the determinant. Or you can try finding the determinant of matrix B. Next is solving system of equation using the Cramer's rule. This is one of the application of determinant. We use the Cramer rule to find the to solve a system of linear equations. And in last semester we showed how to solve a system of linear equation using substitution, elimination. So here, if you have, you can use Cramer's rule to solve a 2 by 2 a system of equation, which is 2 equations, 2 unknown simultaneously. So here we have a system. Solve the following system using Cramer's rule. We have 3 unknowns, 3 equations. We can use elimination, we can use substitution, we can use the row operation, but we want to show one of the application of determinant to solve, which is Cramer's rule, to solve this system of equation. So we have 2x minus y plus 6z equal to 10, that is the first equation, minus 3x plus 4y minus 5z equal to 11, 8x minus 7y minus 9z is 12. So how do we do it? Remember, last time we showed how to multiply. We showed how to multiply 2 matrices. So this system can be represented in this form. This matrix is the matrix of coefficient. If you look at the coefficient of the variables, the first equation we have 2 minus y plus 6z. The coefficient of x is 2 there. If you look at the first entry is 2. Coefficient of y there is minus 1. You can see the next entry is minus 1. If you look at the coefficient of z in the first equation is 6. So you look at the coefficient of the variables and you generate the matrix of coefficient. If we multiply this matrix of coefficient times this column vector, it will take us back to our system. You can try it. Multiply this matrix as is given here in the slide, multiply this matrix times this column vector, which is x, y, z, equal to that. If we you do the multiplication, it will take you back to your system. Matrix of coefficient here is 3 by 3, while this column vector is what? Is 3 by 1. So the number of columns of the first matrix is equal to the number of rows of the second matrix, so multiplication is possible. Please try it. Make sure that you have 2x minus y plus z, and the next one minus 3x plus 4y minus 5z, 8x minus 7y minus 9z. So this matrix that I name A is called the matrix of coefficient. How did I get it? I got this matrix from the coefficients of the variable. The first row is the coefficient of the variables in the first equation. Second row, coefficient of the variables in the second equation. Third row is the coefficient of the variables in the third equation. So A here is called the matrix of coefficient. So according to Kramer, this rule, to find the variables, this A is our matrix of coefficient, like the mother matrix. The formula is given by x is ax, determinant of ax over determinant of A. That will give us the value of the variable x. Y is the determinant of the determinant of the matrix AY over the determinant of the matrix A, and Z is the determinant of the matrix AZ over the determinant of the matrix A. So how do we get this AX, AZ, and AY? If you look at it, the system is matrix of coefficient times the column vector is equal to the constant on the right hand side. This matrix A is obtained by removing the column of variable x. If you want to find ax, remove the column of the variable x, replace it with the values in your right hand side. In our right hand side, we also have a column matrix. Remove the values of the variables of x, replace it by the values on the right hand side of your equations. I highlighted it with a red color. The values in the right hand side are 10, 11, and 12. That is the first equation equal to 10, second 11, the third one equal to 12. To find ax, remove the column of the variable x, which is the first column, replace it with the matrix, the column matrix on the right hand side. So as you can see here, where ax is 10, 11, 12, I have removed the column of x and replace it with my right hand side, 10, 11, 12, and the rest of the matrix is part of the matrix of the coefficients. So AY also remove the column of y, place it with the right hand side. AZ also remove the column of z and replace it with the right hand side. So after doing all this, the determinant of matrix A is minus 141. If you follow the same procedure we did for finding the determinant of a 3 by 3 matrix, you will get 141 minus 141. AX, the determinant is minus 1499, AY is minus 1492, and AZ is 16. So remember, to get matrix AX, remove the column of X, replace it with your right hand side. To get AY, remove the column of Y, replace it with the right hand side. To get AZ, remove the column of Z, replace it with the right hand side. So therefore, X will be determinant of AX over the whole determinant of coefficient matrix. Determinant Y is determinant of AY over determinant of A, and the Z is determinant of AZ over the determinant of A. So this is the values of our variables. So now we can only use Cramer's rule if the determinant of the coefficient matrix is not 0. If you look at it, if the determinant of the coefficient matrix is 0, you cannot use the Cramer's rule, because you are going to divide whatever you get with 0, which is not defined. So the Cramer's rule is valid only if the matrix of coefficient is not singular. If the matrix of coefficient is singular, then the Cramer's rule fails there. So you use another method, elimination or other methods. So we can only use it when the determinant is not 0, determinant of the coefficient matrix. So that is it. We we have finished with the matrices, determinant. So inverse is left for you as an assignment. You can try it. If you have any difficulty, you can let me know. Inverse of a 2 by 2 matrix is simple. The inverse of a 3 by 3 is more complicated, but if you check it, if you study it well, you can do it. So do it as an assignment, send it to me, and I will check it. So inverse of a 2 by 2 and a 3 by 3 matrix. So with that, we have finished with matrices. So now we are going to start directly with functions, because we need to know what a function is, how to evaluate the value of a function at a given point, because after the function, we will start with limits, continuity, differentiation, and integration. So now, what is a function? A function is a relation that uniquely associates members of one set with members of another set. If you have a set here and you have another set here, function will relate the elements of set A, let's say A, with the elements of set B. So a function is a relation, or is a map that uniquely associates members of one set with members of another set. So several notations are commonly used to represent functions. The most rigorous notation is if f is a function which maps x to f of x. So you have a set A and you have a set B. This function picks an element in A and relates it with the elements of B. So that is why we are saying f of x. Give me an element. I will apply my function on it to give a relation with the other set. So several notations are commonly used to represent functions. The most rigorous notation is this, which specifies that f is a function acting upon a single number or element. That is, if you have only one variable, then that function is a function of one variable. You can have several variables, but for now we are going to just deal with functions of only one variable. We call it a univariate or one variable function. So that is, in brief, what a function is. It's a relation that uniquely associates members of one set to members of other sets. So to be even more precise, a notation like f, if you have a function which maps this r to r is the set of real numbers. It's just an example. You have a function. This function maps r to r. It means it maps the set of real numbers to another set of real numbers. So we define the function here by f of x equal to x squared. So give me any value from the first set. First set, we usually call it the domain, and the other set we usually call it the codomain. So give me an element in the domain. I will apply a function on that element, and the result will be in the codomain. So usually we all know that we use f of x to represent functions, but function is f. F is the function, f of x is a value. but that's what we usually know. F of x is a value, because if you give the value of x, if I apply my function, let's say the value of x is 2, f of 2 will give you 2 squared, just like this example, and it will be 4. So this is how we denote what functions. So f of x given by x squared, it means if you give me a number x, if I apply the function on it, the result will be in the codomain. So domain, codomain. Give me an element in the domain, apply the function on it, the result will be in the codomain. So now we are going to see how we evaluate functions value at given point. If you have a function and if I give you a number or an element, apply that function on it, give me the result. So we want to see, let's say f of f is a function defined by f of x equal to, let's say, 2x. What will be the value of f at 0? That is f of 0. So f of x equal to 2x, give me 0, f of 0, put it will be 2 times 0, the result will be 0. So we want to see how we evaluate this simple thing. So given the function f of x equal to 5x minus x squared plus 4, evaluate the following: f of 0, f of 1, f of minus 1, and f of k. F of x is my function, which is defined by 5x minus x squared plus 4. So solution, how do we get f of 0? This is saying that I have a function defined by f of x equal to 5x minus x squared plus 4. F of 0 is saying what is the value of this function at x equal to 0. So at x equal to 0, substitute x by 0, what will be the result? So x 0 here is from the domain. The result will be in the codomain. So f of 0, if you substitute it in this equation, you will have in this expression you will have 5 times 0 minus 0 squared plus 4, which is 4. F of 1 will give you 8. F of minus 1 will be minus 2, and f of k will be 5k minus k squared plus 4. So this is saying, f of k is saying what is the value of this function at k. So k is just a parameter, we don't know its value, that's why we write it as it is. So f of k will be 5k minus k squared plus 4. So now the function is no longer in the variable x, but in the parameter. If it is parameter, it is in the parameter k. If it is in a variable, it is in the variable k. So f of k will be 5k minus k squared plus 4. Just substitution. Substitute the value of x in the function. So this is this. Then next, limits and continuity. So let's start with what we mean by a limit. So limit is the value that a function or a sequence approaches as the input or index approaches some value. Let's take, for example, I have my function f of x equal to 2x. Okay, let's say the value of x given is 1.5. If I substitute 1.5 in my function, I will get a value. If I substitute 1.55 in my function, I will get another value. As x is increasing, 1.5, 1.8, 1.9, as x is approaching 2, as x is moving towards 2, what will be the value of my function? So as x is approaching some value, what will be the value of our function? This is the idea of limit. A limit is the value that a function or a sequence approaches as the input or index approaches some value. For example, consider the table below. We have a function f of x equal to 2x, and we have the number the x values given here are changing. First, the value of x is 0.9. So what is f of 0.9? If you put f of 0.9, it will be 2 times 0.9, which is 1.8. What is f of 0.99? It will be 1.98. As this value is moving, increasing 0.9999, the value of x is approaching 1. And as the value of x is approaching the value 1, also our function is moving and approaching some value, which is 1.999998. So it is moving towards 2. So as x is moving towards 1, the value of our function is moving to 2. So in this case, we can say the limit as x approaches 1 is equal to 2. It means the limit of our function is 2. Let me repeat it again. We are given a function f of x equal to 2x, and we have some values of x that are changing, approaching some value. The first value is 0.9. What is f of 0.9? Is 1.8. What is f of 0.99? Is 1.98. What is f of 0.999? Is 1.998. So as the value of x is increasing, approaching 1, this function is also moving 1.99 up to 2. So it is approaching 2. It is not necessarily equal to 2, but it is approaching 2. That is why we call it the limit. So as x is approaching 1, f of x will approach 2. So this is an example of limit. So from the table above, we can observe that as the value of x is increasing and approaching some value, which is 1, the function value is also increasing and approaching some value 2. So x approaching 1, x approaching 1, and the f of x is approaching 2. So with this, we can conclude that the limit of this function